I've been at Iowa State University for 12 years, and I also serve as the director of the Prosper program for Sustainable Payment Engineering and Research. And I serve as the ISU side director for FAA Center of Excellence on Pegasus. And I'm one of the entrance researchers as a payment systems research engineer. And thank you for joining us today's presentation. And we're enjoying a nice warm August day here. And the topic is working with heated payments, recent technical advances. And I hope that you will be enjoying today's presentation. And I would like to acknowledge a large number of colleagues from Iowa Department of Transportation, Iowa Highway Research Board, county engineers, DOT engineers, who have been supporting our research efforts and providing guidance and support. We greatly appreciate it. Same thing is from the Federal Aviation Administration side. And we've actually received funded research projects both from FAA and Iowa DOT and Iowa Highway Research Board. And we again appreciate all this support and close collaboration with these large number of colleagues. And I'd like to acknowledge the hard work of the Prosper research team. And this is just one of the pictures. And this was taken 2 years ago when we completed the conductive heated concrete project built at the Iowa DOT headquarters. If you're familiar with where the Iowa DOT is located here in Ames, this is actually one of their main receiving lines from the South 4th Street. And you can see a lot of semis and heavy trucks and other vehicles using here. So that's where we actually installed our latest heated concrete project. And this is one of the images as we wrap up that project. You can see the curing compound on wet concrete as we just wrap up this project. And our research efforts have been actually widely covered by national, international media outlets and magazines. And for example, the pictures here, one of the reporters from NBC, Jeff Russen, and this was actually covered by the NBC Today Show, NBC Nightly News with Lester Holt, and many other news outlets, the local TV and radio stations here in Iowa. And again, hundreds of newspapers and magazines have covered our work, and you're seeing some recent coverage from these, the media coverage. And magazines, again, Engineering Research Record, if you're not familiar with it, is a, well followed and well disseminated, magazine in our field. And they've been actually following our work, and this was one of their, segments on concrete projects to watch in year 2019 and 2020. And I will be following this outline as part of today's presentation. And if you look at the heated payment systems, there are actually 3 main types. The most established one is the hydronic heated payment systems. And in this technology, we are actually circulating a warm, hot liquid through the embedded pipes within concrete and asphalt. And, that fluid could be antifreeze, glycol, that type of a thing, so that it won't freeze during the winter weather events and cause problems. And another commonly used technique is electric heating cables. And then in this technique, we're actually heating concrete and asphalt with embedded heating elements. Usually these are placed at the bottom of these layers. And then, we have to turn the system on, and, gradually that heat, it dissipates and, reaches to the top level and melting ice and snow. So our research efforts in recent years have been focusing on conductive concrete and asphalt materials. In this technique, we are actually incorporating conductive materials within the concrete and asphalt materials and getting incorporated it. And once we pave them and put electrodes and bring whether alternating current or DC power system, and then it will actually start generating heat through resistive heating, joule heating. That's the technical terminology for this, the technology. And that's what I'm going to be mainly focusing about this, since these are relatively new technical advances on this, this topic. It's a very innovative material technology. And the basic components is that I kept this, by the way, very applied oriented so that anyone without any significant, background information can follow and understand this, the presentation webinar. And as you know, the main elements that go into, for example, a Portland cement concrete is that we have the cement, and then we put aggregates of different sizes, larger stones and, the sand, smaller particles. We need to add water, both for workability and to get the chemical reactions going. So one of the main difference between conductive concrete and the regular one is that we also need to incorporate conductive agents. And we do that by incorporating materials like carbon fiber, graphite, the dust form, other materials. We can also use steel shavings. We need some conductive materials that we need to incorporate. In our research, we were mainly using these materials here. And then other things that we are adding is admixtures, for example, to improve the workability of the system, dispersion of the fibers, air content, and all that. So I'm just going to use the terminology econ, electrically conductive concrete. Otherwise, it's mouthful every time we repeat it. So we're trying to lower the resistivity of the concrete and, to make it more conductive. So when we place electrodes into that with these conductive agents, when we turn the system on, connected to power, we can actually start generating heat. And we are using stainless steel electrodes so that there won't be any corrosion or long-term durability issues. So these systems should continue to perform and last, for a good number of, say, the years. So I'm a visual learner myself, and I try to incorporate a lot of visual materials into my presentations, lecture notes. And I like this, there's a drawing here that our research team has put together. And what you're seeing here is a complete concrete pavement system. Starting with the pavement foundation, you have the subgrade layer, and then, then we start putting other layers, sub-base layer, and then eventually we have a base regular concrete layer here. And then we're putting this is the base, sub-base layer. And then this is the regular PCC, Portland cement concrete. This is the regular material. And the top layer here, the shaded gray here, is the conductive concrete. Since we are dealing with snow and ice events on top layer, we only need these conductive materials at the very top. So this kind of technology exists actually quite a bit. And, that we've been doing two-lift paving for a good number of years, actually decades. And that's what it is. And in this specific example, we also have to bring power to the electrodes embedded within the conductive concrete layer. And we do that, as you can see, these red say the elements here represent the electrodes. There's another one here. And we do that by putting a conduit system. And eventually all these are connected to a control system. And we can actually remotely operate this, put it into an autonomous mode. And that's going to be helping us transfer the data through wireless technology. We can actually take it to our, the computers, monitor the system, turn it on and off remotely. Actually, I'm able to do this using my mobile phone. We've incorporated a couple of applications, and we can turn the system on and off. For example, we have an active system installed at Des Moines International Airport. We built that system in 2016. So this is fully automated, remote accessed and operated system. And we can access the cameras, see the melting of ice and snow. We can record that event, take still images, and do all kinds of things. That's how it's operated, and it really makes things very easy. As you can imagine, we need to operate this system during winter weather events, and it will be challenging to travel to the sites if you do this in a manual, the operation. So as I just mentioned, we have applications on airfield pavement sites as well. And as part of the research provided by Federal Aviation Administration, and again, we greatly appreciate all the support provided by our funding agencies. And what you're seeing here is that the amount of power needed in different parts of the country to deal with winter weather events. So since we are located here in Ames, Iowa, for example, if you average it, amount of power density that we need in Iowa to deal with winter weather events, it's about 340 watts per, let's say the square meter. And there's an organization called ASHRAE, and I actually just got that from there, so that this is a peer-reviewed published document. There are a lot of committees with top experts working in the field putting together these kinds of, let's say the documents. And if you go to other parts of the country, for example, if you go to Northwest, you may need a higher power density depending on the wind speed and the rate of snowfall, ambient temperatures, and humidity. These are all the climatic data that we need to take into account. And our research team actually has developed quite a bit of guidance on this area in terms of what factors that go into the system design optimization. And as you can see, we take all of that climatic data, and then if you're trying to optimize your system, for example, what we read the length, width, and the thickness of your slabs, and we can actually determine the level of resistivity needed for a given climatic location, and then to do these electrical calculations, and then it will tell you again what that power density is. And then from here, for example, one thing that we can do is spacing of the electrodes. As you decrease that spacing, then we will actually be infusing more heat into the pavement systems, helping to melt snow and ice events. And then if you go to more moderate climates, we can actually increase the spacing, and then we can still achieve the same result. So this is the flow chart that we follow in the system design optimization. What you're seeing right now is actually an analytical model, a simulation. As you can see, there's actually a video file playing here. And this shows you what we built in the field and animation of that. So without actually spending making any significant investment in the computer environment using finite element technology, we are actually able to simulate field conditions. This is actually a thermal imaging system of the 2 full-scale slabs that we built at Des Moines International Airport. And we are exactly able to simulate this in the computer environment by putting the material properties and the thicknesses and joint spacing and other, let's say the parameters in here. For example, the hottest spot is this electrode here, and we are able to exactly, let's say, demonstrate it. And this shows you the counter maps the warmest spots versus, relatively cooler spots. So that's what it is, and I'm going to be showing you many more images in upcoming slides. And another visual image here in terms of the how this technology is implemented. If you want to see it in stages, in the first step is you compact your subgrade, you put your sub-base layer, and over that, you're going to be putting your dowel bars at the joints, and then you're going to put the bottom layer regular concrete, step 2, and then these red elements are the electrodes, as I was just talking about it. Usually here in Iowa, 3 feet spacing is a good one, and then we can actually go down to 2 feet spacing or 1.5, 1 foot spacing if you go into a very challenging environment with significant amount of snow and ice accumulation, and the high rate of snow and ice, depending on again which locations that were located. And eventually the top layer is going to be placed with conductive concrete. So when this system is connected to power through these conduits and brought it into the control system, and when we turn the system on, it's going to create a electrical potential between this hot and let's say the other electrodes, and then using AC power through that electrical potential, we will actually be generating heat, and that's how we melt ice and snow. So I mentioned to you earlier about our project at Des Moines International Airport, and we work with the operations engineer. Again, we greatly appreciate their collaboration, and you can see the aircraft parked in this area. And this area was going to be rebuilt as part of their rehabilitation efforts, and this was built 4 years ago. And at this time, 4 years ago, we were very busy getting ready for the fall construction. And this is the design. They had 10-inch thick concrete slabs, And as you can see, sorry, these were 7.5 inches. I apologize. The 10-inch one was a different project. 4 inches, the regular bottom concrete, and only top 3.5 inches is the one with, say, the conductive concrete. And we were using 1.5 inch by 1.5 inch electrodes. So we had a minimum of 2-inch cover on top of these electrodes. And it's a 2-lift paving again, and there was a aggregate layer and a subgrade layer. These numbers are related to the airfield pavement specifications. If you're familiar with FAA design procedures, that's what they signify, P541 and all that. So. And like any other project, we had several pre-construction meetings with the design firm, agency, the owner of this project, and and others involved in the say the overall operation of this system. For example, the IT people, how we can actually use their wireless communication there, and you can see our site visits here. And during the removal of the existing slabs, and you can see the rehabilitation work going on there. So we presented our technology, what type of sensors and system that we're planning to use, and a lot of discussions so that everyone is on the same page. These are extremely important meetings, by the way. So, and you can see the contractor starting the work 4 years ago in August, September. And this is the regular concrete. Contractor was doing a lot of nighttime working because of the hot temperatures during the day. They were facing some plastic shrinkage problems, which has nothing to do with our project. It's just the regular challenges that may exist for any project. And as you can see, they got done with this bottom layer. Then we started bringing our electrodes here, placement of those, and then a lot of sensors and instrumentation. Since this was built as a research demonstration project, we had a lot of extra sensors and systems here, which is actually not needed for a regular concrete pavement project. And eventually the top conductive concrete layer brought there, and then you can see the contractor curing, like just white pigment, regular curing material. Nothing was done special about this project other than bringing this conductive concrete. There was no meeting with the contractor himself. I mean, the contractor who does the concreting work. These are readily available ready-mix trucks and other, the small paving equipment that they were using for that project in any way. And this is a control system located within the airport there. And again, here is a schematic view of it. And as I mentioned it to you, this is an image of my mobile device. And you can see during a winter snow event, our heated pavement area is free of snow and ice. There's just this paint here to distinguish it from the surrounding area. We can actually turn the system on and off remotely. We've designed all of this system ourselves, and then it actually transmits all this data to a back laptop, and we back it up on a regular basis. And we have temperature probes, moisture probes, strain gauges, and all that. So December of 2016, that's when we started getting the first round of, say, the winter weather events. As you can see, the first snow events, and it was about 1.5 inches. And I love this picture. It tells you a complete story that if you have heated pavement systems, then you do not need this kind of expensive, let's say the traditional snow removal equipment to keep airfield pavement surfaces free of ice and snow. And this was taken during a daytime. We can actually melt snow and ice during nighttime as well. Sometimes if you show a picture taken during daytime, people may not understand, was that the sun or something else melting ice and snow? Surrounding areas, as you can see, another daytime picture still covered with ice and snow. There are a lot of curious people like this pilot for one of the corporations using their own aircraft and all that, and very puzzled with what's going on in this area, warm and nice and dry and no skidding and sliding issues, and they're free of ice and snow. And here are some thermal images that our team recorded. You can actually see the electrodes like ribs embedded within the system, and the surrounding hangars and other buildings warm as the heated slabs here. And then again, that heat is the one helping us to keep the system free of ice and snow. And the surrounding areas are covered with snow and ice. And here's another picture. There's absolutely no impact to aircraft instrumentation and other, say the devices operating at the system. This system is no different than your electrical appliances like your dishwasher or, say the washing machine or any other, like your computer. We're using regular electrical alternating current with 60 hertz. And many other, again, pictures from different snow and ice events. Keep in mind that some of these events were extremely challenging. We had a lot of polar vortex temperatures as low as minus 30, 35 degrees, let's say the Fahrenheit. Actually, if you go to that level, they are just about the same Celsius, and we were able to melt ice and snow under such challenging conditions. So that was on airport side. Let me help you cover now the highway sites. And again, here's the aerial picture for the Iowa Department of Transportation. And this is again South 4th Street, and this is the Iowa DOT headquarters, and you can see the north direction here. And they were again gonna do a rehabilitation work here. Since this is their main receiving line, there were a lot of slabs shattered with cracks and all that. So they were going to replace these anyways. And then we had a research project starting at the time again, demonstrating this technology. And as you can see, we chose the most challenging area with high, heavy traffic. And this is the heated concrete slabs, conductive concrete technology. And then they were going to replace all these slabs. So the remaining section of the project serves as a control system. And that's where the project is located. So we have two slabs right next to each other, 24 feet wide versus 15 feet every slab, 2 by 5, 10 slabs here. That's how this 24 to 75 came together. And this is where we were getting our power from. There was a the electricity pole located very near the project, as you can see. And we appreciate, again, all the support and guidance provided by the DOT. So since this was done as a research project, we wanted to try different shape of electrodes with different diameters and, the thicknesses and all that. As you can see, we have flat bar, 1 inch, and smooth circular bars with different diameters, 1 inch, 3/4 of an inch, hollow, the circular bars and all that, and the spacing are different for every slab. We have varying number of electrodes. So every slab actually had something unique and different. And if you're wondering about electrodes, and again, here is one of those hollow ones, solid steel ones, and then the flat, the stainless steel flat bars. And so it was actually a very rich research project. And you can see the configuration of the electrodes that we have. As you can see, now you have relatively longer spacing compared to like this slab. We have actually a much shorter spacing because we have here 10 electrodes versus 6 here. And, and other details of the project. And this is where the conduits are placed. And so there are a lot of, again, since we're doing this for research purposes, we had a lot of instrumentation. We did everything ourselves in terms of this instrumentation by closely working with the electricians from the Iowa DOT. And you can see the data loggers and, the temperature probes. And this is our control system that we started putting together in our labs. And then we eventually took everything to the DOT. And here's a snapshot of the notice that the DOT sent it out about this construction project, notification to the public and people working at the agency. And as you can see, these slabs have worn out, and you can see the removal, construction removal equipment there. And they started actually removing the existing slabs as part of this rehabilitation work. And as you can see, they plan to start this work sometime from October to the November 2 years ago in 2018. And they were cutting these slabs and removing them, construction work, and breaking these slabs into these smaller pieces and then taking them out. And you can see the pavement foundation system located right under the existing slabs, and a lot of actually, the organic material, you can see darker color. And we tried to put some drainage there with geofabric and placing base material so that we can actually help improve the long-term performance of these SCADA systems. So as you can see, mid-October, they continued this SCADA construction work. Then that gave us the opportunity, when the existing slabs were removed, we started putting strain gauges and other instrumentation at the site so that we can keep track of overall performance remotely. And we're going to have a rich data set once the system is turned on and off. This is the bottom layer of this, again, existing slabs, and during the regular paving procedure, and we were able to take cores and to understand the strength and workability of the regular concrete as well. And as you can see, air content and slump, our research team were documenting this in addition to the other quality control and assurance work that was going on at the plant and at the construction site. And we are marking the location of our strain gauges and other sensor instrumentation system. And you can see the control section now. This is not the heated pavement area. It was just regular brooms finishing there. And then eventually, once the bottom layer is done, we were able to get there and finish the installation of the conduits, since these are going to be embedded under these, the slabs. And you can see again the bottom layer, regular paving construction, which is covering our instrumentation at the pavement foundation system and other places. Concrete was delivered by ready-mix trucks. And again, the updated construction schedule. Once they were done with this removal of these surrounding areas and all that, these are the areas that we are embedding our conduits on the other side of the slabs. And so we started, as you can see, in late October, going to the plant, concrete plant, and understanding how they produce concrete and what is the best way to actually mix the conductive agents. These are the fibers that we are incorporating, these darker colors, in the ready-mix truck and when they produce conductive concrete. And here are some images from our earlier projects, how it's produced and all that. And we had a lot of samples at the site to take, the samples and understand the conductivity and other properties, air content, slump, and all that. And as you can see, everything was meeting the specification, so it was good quality concrete. So during the day of paving, since this was done in two-lift paving, this is a regular concrete surface, it had to be cleaned very nicely so that we can achieve a good bond between the existing bottom layer and then the top layer that will be delivered to the site as conductive concrete, and getting our cables embedded and all that stuff. And now you can see the placement of the stainless steel electrodes at this site. And again, it was our research team members doing these installation. And we appreciate the great guidance provided by the DOT facilities manager, Mike Harvey, helped us. Some of these electrodes were longer than, the slab width and length. We had to bring them to the right length, some small, the additional work at the site. And you can see again the spreading of the electrodes at the site. And this is a nice picture now. All the electrodes are installed and ready for the top conductive concrete, and we just secure them to the existing slab so that during the placement of the top conductive concrete layer, none of these electrodes will be moving and causing any potential problems. And additional instrumentation for the top layer, we call them sensor trees. We put a dowel bar here and attach the temperature probes at different lengths. And we use these kinds of non-conductive materials so that like fiberglass, and there won't be any problems when we turn the system on with presence of the alternating currents, and placement of the conduits with the assistance from our colleagues from Iowa DOT. And getting ready, and as you can see, you see many cables here because we have, say, like 7 temperature probes, and each one of them is connected to the data loggers using these cables. And last, the pieces of the sensor instrumentation work and getting ready for the top layer construction, and a final cleaning there in late October. And now on October 25th, you can see the top layer conductive concrete. And again, using this vibrating screed, nothing special. Contractor was using this for the regular concrete anyways. And again, there was no extra training required, no additional, information needed to be shared with the contractor. They are able to come and, they work it out and place it like any regular concrete there. So, and you can see the nice, the finished surface of the concrete pavement system. And again, they were just using these, the brooms for roughening the surface, for surface characteristics. And again, we just cure this using the regular curing compounds and like any other regular concrete. And as you can see, the conduits on the side of the, concrete pavement systems here. And again, the slabs are, say, 12 feet in width and 15 feet in length, and this area is 75 by 24. And, we were just monitoring the area. And then we just needed to go there later by the end of October and, do some small additional work here, protecting our sensors and all that from this hot mix asphalt placed on the side of the roads as part of the DOT's design. And, the soil cutting and cleaning the joints. And again, just regular, the procedure and sealing the joints like any other concrete pavement project. As per the agency's request, we also ordered the shed, work with them, get it delivered to the site, and so that control system can be placed in there, and then during the research operations, we can actually use this area to monitor the site. We greatly appreciate it, as this system needs to be run during the winter weather events. And our research team is just wrapping up some final moments and bringing all these temperature and moisture and strain gauge cables into this control unit here at the DOT. And again, we were working with, along with the DOT electricians, we had collaborators from electrical computer engineering, and our research team has quite a bit of capabilities in this area. And we put a programmable logic controller, a smart PLC system to operate this system remotely and manage all this data and save it in a laptop in a remote manner. And you can see as the work progresses there, relays and other electrical details there. And, this is actually a three-phase system, and we're using we are using 220 volts at the site. But our system can be run with 110 or, 480, 360, whatever is available at the site. And the lower the voltage obviously is better for safety purposes. And then the agency made it available 240, and we were able to work with it. So eventually, as you can see, when we had the late 2018, when we had the first snow and ice event, and you can see a nighttime operation there, we were actually bringing even additional snow, dumping it on the heated concrete slabs here, and we are able to melt it away very nicely. Not only it melts it, it actually dries the surface, so there won't be any slip and fall incidents, and there is no need to use the de-icing chemicals, which really helps us in terms of the long-term, the performance and environmental, there are many environmental benefits, and this is definitely a sustainable winter maintenance alternate system compared to the traditional snow and ice removal techniques. So I believe that this picture is worth 1,000 words, and you can see a close-up picture of it during a winter weather event. And some additional images. You can actually see the location of the electrodes here on these areas, and that's where the heat generation starts. But soon after that, it actually has a uniform heat generation on this top surface. To create contrast, we on purpose turned only these 4 slabs on here, and then left other places, they let it accumulate snow and ice, so that you can see this sharp contrast between unheated areas versus conductive heated concrete. And as you can see, it works, and it provides you a safe traveling platform and free of ice and snow, and it eventually dries the surface. And again, it mitigates and eliminates the use of de-icing chemicals, which actually help you extend the life of the infrastructure system. And I point blank ask to the colleagues who does decades-long field work and working with pavement systems throughout their life, and they tell me that they expect to see about 20% increase in the overall design life of these systems due to the elimination of the de-icing chemicals. For example, if you design your concrete pavements for 30 years performance, with the inclusion of the conductive concrete and elimination of the de-icing chemicals, we can extend the life to, for example, additional 20%, 36 years. So that's how we need to look at it. And again, here are some additional, say, the thermal imaging systems with our high-quality sensitive thermal camera. And it actually captures regular image along with the thermal imaging system. You can see again the same image captured by the same camera. And you can hardly see the building in the background here with a naked eye. But as you can see, the thermal imaging system is capable of capturing where the windows are. You can actually see where your most of heat losses is taking place and how fast the heat generation is taking place in our conductive concrete. And these are twin images. One is a thermal imaging system, and other one is the regular image. And you can see a very, the stark contrast between unheated areas versus heated areas. So, and then we had many more snow and ice events, and as you can see, we have a good documentation of them. So when we document a snow and ice event, we record all the humidity, precipitation, and how much snow and ice we get, and air temperature, and all of that information is recorded. And as you can see, when you turn the system on at different times, and we do all kinds of different operating procedures for this, and then you can see a fully melting process, whatever all the snow and ice accumulated on it. And as you can see, this was actually at this time more than 2 inches of snow accumulated at the site. What we're trying to say here is that if you want to achieve a snow and ice-free system, and if you know when a certain snow and ice event is going to get to your facility, it is best if you turn it on for about like 2 hours in advance, so that you can actually achieve a warm enough slabs that nothing else is going to accumulate it on it later on. But to achieve good images, mostly we actually let it accumulate, and then we turn the system on so that we can actually have continuous video recordings of how the snow melting process works out. But in a smart operating system is going to be turn the system on in advance, then once you achieve warm slabs and nothing is going to be accumulating on it. So again, now we're doing a third phase of this project with the city of Iowa City. As you can see, we have done demonstrations on the airfield pavement side, highway pavement side. Now we're doing a bus stop project in Iowa City. It's actually at the early stages of it. If you're familiar with the Muscatine Avenue, and there's a unprotected bus stop area, they want to close this area. Here is where the bus stop shelters are going to be located, and some surrounding areas are going to be heated as well. And again, here's the opposite of this across the street, and some additional areas for ADA capabilities and all that. And sometimes we get questions, are there any safety concerns, when you have conductive concrete like this bus stop platform, for example? What if someone touches the slabs and all that? Obviously, we're not recommending that, and no one should go out in the middle of a runway or a highway system or a bridge, with trucks and other vehicles on it, try to touch it. But just in case there are some concerns of that kind, what this graph shows is that if you actually put a primer and a regular paint, thermoplastic paint, you can actually eliminate any potential voltage to such levels that you can actually hardly detect it, like 0.05 volts. Keep in mind that any battery that you have is like 12 volts and more. So as you can see, there's a significant reduction that we are achieving once you put a, let's say the thermoplastic paint on it. So there are some really easy ways of actually providing a much safer environment if there are any concerns of this kind. So I want to make sure that we have actually enough time for questions and the discussion. So what I'm going to do in the next couple of slides, I'm going to summarize our discussion so that we can have enough time for our discussions, question and answer session. And as you can see, the biggest gain here is the safety, and which is priceless, right? And so we are actually achieving a very safe surface with the use of this technology. And there are a lot of benefits, again, associated with it. And again, reduces the amount of labor and equipment costs associated with winter maintenance activities. When we do the benefit cost analysis, even for Des Moines International Airport, we have actually shown that with the implementation of the heated conductive concrete technology, benefits are eventually going to outweigh the costs. So when we do a life cycle cost analysis or life cycle benefit cost analysis, say like in a 20-year period, benefits are going to outweigh the costs associated with flight delays, slip and fall incidents, and skid off and things like that. And there are a lot of costs associated with winter weather events. People may not realize that, but for example, in an airfield pavement environment, airport, airports have to collect all this contaminated slush, snow and ice. They have to build the treatment facility, which is out of the ways. Most of the times they are actually in underground facilities. Our research team visited Minneapolis, St. Paul international airports, and you cannot believe how large of an area that they have under the airfield, system underground, and significant amount of costs are associated with the treatment of this snow and ice after the use of de-icing chemicals. And there are a lot of problems associated with the use of de-icing chemicals, corrosion of the vehicles and lighting fixtures, and the damage to the vehicles and all that, damage to the environment. As you go down in Mississippi, once you make it all the way to Mexico Bay and New Orleans area, there's significant amount of pollution is taking place, and there's harm to the living organism and fish and other in the rivers and water systems, and damage to the environment. So it's just a significant amount of impact, adverse impact on the environment. So and also, if you do a sustainability study with the use of traditional equipment, significant amount of fossil fuels are being used, and a lot of the agencies like airports, they have to actually have quite a bit of equipment. They need to house them, maintain them. They need to have large garages. When we visited Minneapolis St. Paul International Airport, they have to have 85 people around the clock in 3 shifts, stay at the airport, get ready for any snow and ice event. Those are significant costs that the agencies have to cover. And, they have these gigantic kitchens and barracks to house all these, the workers and people at the site. So when you look at in a holistic perspective and do these calculations, and it's stunning, the costs associated with the traditional snow and ice events. So this provides actually an innovative, way of dealing with these, the winter weather events in a really sustainable and environmentally friendly manner. And again, it reduces the greenhouse gas emissions associated with these technologies. And there are actually many, many fold benefits that, we can talk about more. And here is the image when NBC Today Show came and visited us just over 2 years ago. And, the airport managers and camera people. And this is Jeff Rossen from NBC Today Show and NBC Nightly News. And I'd like to, again, specifically thank Bob Uni. He's the director of the Maintenance Bureau from Iowa Department of Transportation. And Mike Harvey, he's the facilities manager for Iowa DOT. And I cannot thank them enough for all their support and guidance for our research studies over the years. Iowa Department of Transportation, Iowa Highway Research Board, and Federal Aviation Administration, and City of Iowa City and all that. So here is my contact information. I'm just going to stop here. I have some video clips if you have additional time that I can try to play. But I will be very happy to answer any questions and comments that you may have. And we have a prolific research team. And my research team has produced over 400 publications within the past 18 years. And on this, the heated concrete and asphalt alone, we have more than 50 peer-reviewed publications. And if you type my last name, pronounced as Jaylan, and Kidit Payment, and you're going to see thousands of articles and news coverages and all that. You can easily have significant amount of resources available to you on the, say, the web. But here is my email address, and this is my phone number. Please feel free to send an email and give me a call, and I'll be happy to answer any questions that you may have. And again, thank you for joining for today's, the webinar. I'd like to thank Keith Knapp and all the other colleagues from Iowa LTAP program for kindly inviting me for today's, the webinar series. And I hope that you enjoyed attending this webinar. Thank you.
Thank you, Halil. Appreciate it. If you want to stop sharing, the chat pod will pop up for everybody. It just maybe be a bit easier. We do have, so everybody, if your chat pod is not initiated, up in the upper right, there's a little chat icon that allows you to chat questions to Halil, or there's even a little hand in the participant panel that you can raise your hand. I could put a small group here. I could probably just unmute you and you could ask questions too verbally if you want to do that. Halil, we do have a question here. My chat pod is really small, so I'm trying to, has ISU and the Iowa DOT been able to locate a test section out on the system somewhere in Iowa? If so, is there any preliminary test data to share?
Okay, so what I shared with you is the data so far is the one that we built at the Iowa DOT headquarters located here in Ames, Iowa. And so that was the second phase of our project. We started with the Des Moines International Airport, sponsored by the Federal Aviation Administration. So we have not been able to try it on a highway system anywhere else yet, but I know there are a lot of interest on, for example, shoulders, where you have high traffic with significant amount of trucks operating in that area. It's a safety hazard. Try to go clear ice and snow in those areas. Rest areas is another excellent, example. The most congested, critical areas, those are going to be ideal spots for this kind of implementation of this technology. So in the third phase, we're taking this to City of Iowa City into the, the bus stop shelter area. That will be the next demonstration project that we will be doing. So I hope that I answered your question. And those are 3 demonstration projects that have been going on for the past several years.
Mm-hmm. Okay, if anybody, again, has any other questions for Halil, you can either chat to all participants in the chat pod, or again, there's a little hand under the participant list. You can click that, and I will unmute you. That's another option. As you were talking about the Gulf of Mexico, Halil, it dawned on me that the last time I was in Alabama giving a safety presentation, a safety and maintenance presentation, a significant number of the questions were about actually ice control in the South, because a lot of them are unprepared for that, but also are able to construct most of the year. Yeah, this seems like it would be something that could apply down there too.
Absolutely. Actually, I can tell from one of my own experience. Several years ago, I was invited to give a talk on roller compacted concrete to Dallas, and I did that also, but I was flying at the time, but before then, for some other collaborations, I had to try, as I had to take samples with me. That's like 13 hours, 14 hours type of a drive. That south, there was a ice storm came, and they had to shut down the entire airport, and I was stranded at the airport. I could not come back. My wife couldn't believe it. She was saying, like, my God, you're that south, and it's that bad. But as you mentioned, that ice actually poses a significant challenge. If they actually have this kind of technology, that ice can be very easily handled. And, keep the critical infrastructure system like major international airports safe and open. And the bridges, by the way, bridge decks are another prime spot, and we have a lot of interest here in Iowa to expand this technology into those areas as well in the next phases of our research studies. So those are going to be some really prime areas. Sidewalks, for example. Again, the more congested and heavily trafficked the areas are, the better candidates they are. And I mentioned to you, for example, the rest areas. There was a heartbreaking scene earlier this year. a pregnant, the city driver got stranded and in a rest area, and then other, the people in the area traveling there to come and help her, the city get her vehicle moving and all that in a van. And actually, if you have this technology installed into those areas, we can actually easily keep those areas free of ice and snow, and so that we can continue to have safe operations and keep the infrastructure system open and accessible. So in Iowa alone, we get about, more than 4 million people visiting our rest areas during winter weather events alone. So we had more than 16 million people visiting rest areas on a yearly basis. So if we keep these points in mind, the potentials for this technology is actually huge.
Yeah, I was just, as you're talking, I'm thinking of all the sidewalk work zones and things like all the potentials here that could be true. So does anybody else have any questions for Halil? Chat or raise your hand if you could.
As we are waiting, ADA, the city compatibility issues, American with Disabilities, ramps, ADA ramps and all that in those areas with people using, the city parking spots for, the people with disabilities and all that. I believe that those areas, again, are another prime spot so that they don't worry about any, ice and snow additional challenges in those areas during winter weather events.
Absolutely, and I do ADA training and for curb ramp and whatnot, parking spaces, and oftentimes those are exactly the locations where there is snow accumulation or ice accumulation because it's hard to get the drainage to work right in a lot of those areas. And yeah, this would be perfect. Okay. Well, again, we're not getting any other questions. Again, I thank everybody for joining us today. We have, as I mentioned, we'll send the certificates of attendance to everyone, and we do have another training on pedestrian safety countermeasures in a couple of weeks that you're welcome to join and register at the iowaltap.iastate.edu website. And again, thank you everybody for joining us today. Be safe, be healthy, and treat everyone as an essential being, and we'll all be okay. Thank you, Halil. Thank you, everyone.
So thank you. Happy Friday. Have a great weekend. I appreciate everyone attending today's presentation. I greatly appreciate it. Thank you.
Thank you. Bye-bye.